Here we go. Okay, welcome everybody to our weekly seminar series at the Department of Marine Geosciences. And we are very honored to host today Professor Daniele Giordan from the Research Institute of Geo-Hydrological Protection in Italy. Daniele, thank you very much for being with us, even that it's through Zoom. And you are closing our semester, by the way. So some words about Daniele. Daniele completed a master and a PhD in earth sciences at Torino University, where he studied deep-seated gravitational slope deformations, large landslide monitoring systems, and early warning procedures. He started working at the Research Institute for Geo-Hydrological Protection of the Italian National Research Council in 2004, becoming a scientist and a scientific researcher in 2009 and a senior scientific researcher in 2021. Scientific coordinator of geohazard monitoring group since 2015. He works in particular on the development of new methodologies and systems for geohydrological processes monitoring. He focused his attention on the use of monitoring systems for the improvement of the geological model of large slope instabilities and the correct management of early warning system. Recently, he concentrated his attention on the definition of a communication strategy for the correct management and dissemination of slope instabilities monitoring results. Since 2017, he is chairman of the Commission C35 monitoring methods and approaches in engineering geology applications at the International Association of Engineering Geology and the Environment. Since 2018, a member of the advisory board of the Interdepartmental Center for Service and Robotics of Politecnico of Torino. Since 2020, member of the advisory board of the Research Institute for Geo-Hydrological Protection. And since 2022, a member of the executive committee for the IAEG. He authored more than 100 indexed scientific publications. So with this background, we are very honored to host you with us, and he's going to talk about unmanned aerial vehicles for geohydrological processes, characterization, and monitoring. Thank you very much, and the podium is yours.
So thank you for this introduction and this invitation that gave me the possibility to show some research activities that are related to the use of a unmanned aerial vehicle for the study of geohydrological processes. So just a few words. So the National Research Council in Italy is the most important public research institutions that we have in Italy. Is divided in several research institutes, and I work for the Geo-Hydrological Protection Research Institute, of course. So we do research, but we are also a competence center of the National Civil Protection Agency. That means that we are called to support from the scientific and technical point of view the National Civil Protection Agency when we have a large emergency. Our field of expertise are, of course, geohydrological instabilities. That means mainly landslides, but also we are studying river dynamics, debris flow, and glacial risks. In this presentation, I will show some results and some experience that are dedicated to the use of UAV for the study of geohydrological instabilities. We will start with a short UAV description about, just an introduction, some important points, and then I will show you some examples of the activities that we are doing with this system that unfortunately now are also known for the use during conflict and wars, but of course in my presentation we will focus the attention of the use to support the science. So probably you are better familiar than me, but just to introduce that when we are thinking about the unmanned aerial vehicle, there are many possible solutions. also balloon and airships or kites can be considered, and many air vehicles. In particular, usually the most adoptive system are these, so the fixed wing solution or multi-rotor solution. Okay, so these are the two most common. When we analyze how that works, if we are considering a multi-rotor, you see you have several engines, okay, and several propellers from 4 up to 8 or even more than 8 propellers. Then, of course, inside there is an electronic system that is able to manage the flight of the system, using usually also a GPS receiver that control the position of the system, and of course a gimbal that is managing the camera. Just another very, very simple example of fixed wing. So fixed wing are more simple, considering the systems and the elements of the systems. There is usually a single propeller. Nowadays, there are also hybrid solutions that have the possibility to make it vertical takeoff and then flight as a fixed wing. Yeah, but so the market is very, very large. There are many, many solutions. Since we are working in particular for the study of Geo-Hydrological protection, so we are working on landslide or other processes that we will see in the next part. The use of UAV is, so the UAV are just carrier, okay? And what is the importance is the possibility to carry something, and in particular, their possibility to carry a payload that could be a camera. Very often this is just a visual camera, okay, so RGB camera that could be a common camera that you can buy also on the mall, yeah. Or there are also other possibilities that are cameras that acquire in a different spectrum, okay? That could be UAV camera or near infrared camera. So there are many, many possibilities. The other important added value, in particular in the last years, is the possibility to install on the UAV also a small LiDAR. The LiDAR is a system, is a laser, is a laser scanner, so is a system that is able to acquire a point cloud and to create a 3D model of your area of interest. Of course, since these are bigger solution, you need more important and big UAV, but nowadays commercial UAV are able to carry also this LiDAR. To acquire what and to do what? To finish the introduction, just to fix some points, probably you are familiar on that. The aim of this acquisition is usually, as I mentioned before, the acquisition of point clouds, okay? And these point clouds can be used to create a digital surface model, like in this case. So in the upper part of the figure, you see a point cloud. This is, of course, a section of the point cloud, an example, and you see that this point belongs to the ground, but also to the other elements that you have on the ground. Okay, this digital surface model can be useful for many activities, but usually when we are studying the ground and we are studying, for example, landslides, the most important data is the digital terrain model. You see in the second part of the figure, just the points that belongs to that belongs to the ground, and using this point, so without the other points that are not, that do not belong to the ground, we have the possibility to obtain the terrain model that is usually very important and useful. Then once we have the possibility to obtain this point cloud, we have many representation. Okay, we can create a grid with a predefined space between the points, or for example, the creation or FTIN, okay, so a triangulated irregular network, that is another representation of the surface that can start from an irregular network of points that is usually the results that we have using an UAV. Nowadays, we are working a lot, not only with just with the point cloud, but we are coupling the point cloud with the color. Okay, that is very important to have a sort of realistic representation of our area of interest. And in particular, in this image, you can see an important difference between a point cloud and a mesh. Okay, so on the right, so on B and D, you can see not the point cloud. Okay, that is a sequence of points that represents our area of interest, but what we call a digital outcrop model. That means that we have a continuous representation of the elements that we want to study. The added value is quite evident in this image, because you see that you have a better representation of, for example, this outcrop. Okay, and inside this outcrop, you can recognize, and we will see in the next part of our representation, we can recognize, for example, several discontinuities that are not so evident considering the point cloud. So this solid image that can be created starting from a sequence of image acquired by the drones, I think that can be very useful for the study of rock falls or cliff, yeah, and to have, for example, a good characterization of yeah, the main characteristic of the outcrop. I mentioned a sequence of images. Another important element that is very useful when we are using a manned aerial vehicle is the structure for motion. Okay, so structure for motion, I don't know if you are familiar with this family of algorithms, are a very interesting family of algorithms that are able to create a 3D model, okay, a network of points that make this three-dimensional representation of the elements that we are studying, starting from a sequence of image acquired from different points of view. Okay, so as the name, structure from motion, it means that you have the possibility to create a three-dimensional structure from a sequence of image. This is very useful. The structure for motion is not just linked to UAV. If you have a smartphone, for example, and if you want to create a 3D model of an outcrop, you can do it even without an UAV, but just moving yourself and acquiring your outcrop, for example, from different point of view. There are many rules to acquire images that can be processed using a stratum motion approach. So as I mentioned before, the motion is required. That means that, for example, if you want to acquire a room like the one that you see in the upper part, okay, you need to make many pictures, okay, moving all around the room. Or if you want to acquire an object, again, you have to move around the object and acquire a very, very huge sequence of image. An important element is that the overlap between images should be more than the 60%. This is an important point, okay? Then this is a quite typical overview. Okay, once you have acquired the image, all the stratum motion softwares work more or less in following the same workflow. So there is this pre-alignment procedure. We will see an example in the next slide. Then the generation of a sparse cloud, and then the generation of the dense cloud. And once you acquire the dense cloud, then you can, for example, create also an orthophoto or, for example, a digital outcrop model. Just to make an example, you see this small Earth dam, okay? This is a small research project that I did a few years ago. In this image, you see every line is the position of a single image acquired by the drone. Okay, you can see that the drone flight following several scan lines. Okay, you can see also that the drones flight at two different elevation altitude. At two different altitudes. Okay. Since the drones usually has a GPS, there is the possibility to acquire also the position of the picture taken by the drones, okay? And the software are able to import also these GPS data. Okay, so according to this sequence of image, you can see the creation of the first point cloud. You see that this is very, very roughly. Then you can move from the first level point cloud to a dense point cloud, and you have the possibility to create this model that is a digital surface model, and at the end to obtain your digital image, okay, your three-dimensional image that you can see in this representation. In the representation, you can also see several flags, okay? All these flags are ground control points. The use of ground control points is very important to improve the accuracy of the georeferencing of the model that we are creating, okay? To be more detailed, this is the approach that can be used when we have to design a flight path, okay? Or if we are using, for example, a smartphone, so without the UAV, we have to use more or less the same approach. You can see in these flight paths, every red point is a position where the UAV acquire an image. The distance between these points are related to the area that the camera is able to acquire, and the distance should be considered that, as I mentioned before, the frontal overlap to obtain a good data set that can be processed using the stratiform motion algorithm should be over the 75%. That means that in two images you are acquiring more or less the same area, okay, just with a small change of position, okay. So there is a very large overlap in the direction of movement that is called the frontal overlap, and more than the 60% in the side overlap. That means that if you have two skylines, so this area should be more than the 60%. It means that you have to acquire a very high number of images, but using this very high number of images, then the stratiform motion algorithm works better, and you have the possibility to obtain a good model. Of course, if you are flying, for example, with a multirotor, you have the possibility to fly it all around a single element. It could be a building, but could be also an outcrop, a cliff, or something like that. A very interesting possibility is to change the angle of the camera. You see in this example, two different flight paths at two different heights with different angles, and this can be very useful to obtain a complete acquisition of the elements that you are studying. An important element that should be considered when you have to plan the flight path is the ground sampling distance, okay? This is a very simple formula, starting from the dimension of the sensor of your camera, okay, and it means also the resolution of the camera. And considering the flight height, okay, if you want to obtain a particular resolution of your ground, you can estimate the flight height, okay? And of course, the distance between the camera, that means your drone, and the topography, okay? So this is very important. Just to make an example, usually when you are working with a drone, like, I don't know, a very common DJI, the flight altitude range from 40 up to 70 meters to have a very good resolution. It depends from the camera, but if you are flying at 40 meters, usually the resolution is more than 10 centimeters of your ground. That is, of course, a very good resolution. As I mentioned before, we will see also in some example, the use of ground control points is quite important to have a better geo-positioning of the model. In particular, if you are working on slopes or on very particular area that are characterized by a strong change in the altitude, a good distribution of ground control points at different altitudes are important to attain a very good model. Of course, the last generation of UAV are very often equipped with a real-time kinematic correction that improve the quality of the GNSS and decrease the number of ground control points that we need to have a good model. Some example of application, I'm working in particular with landslides, and in the past we publish one of the papers that we publish on landslides is this very simple workflow. Yeah, it is quite evident that if we are working with steep slopes, a multi-rotor solution is probably the only solution that we can use. As I mentioned before, with the multi-rotor, we can fly just in front of our rock slope and acquire from different position all our outcrop. Once we have the model, then we can use some application to identify the discontinuities that we have in our outcrop, and starting from the orientation of this discontinuity, evaluate the rock stability. On the contrary, if we are working on gentle or moderate slopes, the use of fixed wing solution can be very useful, because fixed wings are faster and they can cover larger area. Once we have, for example, a model, we can create an orthophoto and use the orthophoto to map the landslide and to follow, for example, the landslide evolution. Okay, so starting from this gentle slope, this is an example in Collazzone. Collazzone is more or less in the center of Italy. Just to, I'm working in Torino, so in the northwest of Italy, more or less in this position. In the center of Italy, there is another office of my research institute, and together, a few years ago, more or less 10 years ago, we made this survey to evaluate how we can use UAV to map recent landslides. So we study also the possibility to map the same landslides using different approaches. That in particular was the UAV, satellite image, also field morphological mapping, and this GPS RTK that you can see. These pink points are the limit of the landslide. That is our benchmark, so our ground truth that we acquire using this GPS RTK solution manually. Okay. Then, for example, we can use satellite images. You can see this example of world view in false color or in true colors. Okay, so these are two possible applications. Again, the UAV, and you can see that the detail of the UAV is very, very high with respect to the satellite. At the end, this is what we obtain. So this is the same landslide, okay? But if we try to make the limit of the landslide using different approaches, of course, we obtain different results. And in particular, you see that there is a good response considering, for example, the limit of our benchmark. There is the GPS RTK, so the black one, with the world view and in true color, monoscopic or stereoscopic, but also of the UAV. Okay, so the point is that if we want just to make a fast mapping of the limit of the landslides, it is not always mandatory to have a very, very high resolution of our model. We see in the example that I show you in the previous slide that also the use of satellite image that has a resolution of a couple of meters can be useful for the identification of the limit. Then, if we need to study the landslides and to study also the characteristic of the landslides, of course, we need a higher resolution. And from this point of view, the use of UAV that can acquire more detailed sequence of images when we need can be a very, very good solution. And this is quite evident, in particular, if we want to work with steep slopes. And this is an example. We are in the north of Italy, so this is a rock wall. No, this is a rock wall not far from these houses, you see. A few years ago, from these rock walls, we had some failure of some blocks that arrive very close to the houses. So the point was to evaluate the possibility to have other unstable blocks in this area. You can see that it is a quite large area. It is not easy to assess this area. So also because the presence of possible unstable blocks. So the point was, are we able to create a very detailed model and use this model to study our outcrop? So in this video, I hope you can see, a digital outcrop model. The resolution of this model is 5 millimeter per pixel. You see that this is a very, very detailed model. You can obtain this model flying very close to the outcrop. I was the pilot of these of these acquisitions, so it has been a very, very stressful flight, but at the end we obtained very, very good results. So starting from this model, we have the possibility to, for example, identify all the discontinuity that belongs to bedding and also to other families of discontinuities. And at the end, you see, we can have a good identification of all the discontinuities, also in area that can be quite hard to reach and measure, for example, manually. Okay, so this is another example. You can see that with the UAV, we have the possibility to fly all around our outcrop and make a good identification of the position of discontinuities. Then recently, working with my colleagues of the University of Pavia, we developed this code that is called ROCA, and ROCA is a code that is able to make a Markland test of a digital outcrop model. So this system has been designed to using the Becker disk. So starting from this point cloud, we have the possibility to identify an area that belongs to a discontinuity, and then the system create several disks that are a representation of the discontinuity. To be more clear, this is an outcrop that we use to develop our system. Okay, you can see in this outcrop the presence of several discontinuities. Okay, not only the bedding, but also orthogonal discontinuities. And this is the identification of the discontinuities on the digital outcrop model. And starting from these discontinuities, these are the Becker disk that the system is able to create. Okay, you can see also that the dimension of the disk change according to the dimension of the discontinuity that has been mapped on the digital outcrop model. Once you have these discontinuities, it's quite clear and evident in this image that you can also consider the intersection of this discontinuity, and yeah, this is another representation of the same outcrop that I described at the beginning of this part of the presentation. And according to the presence of this discontinuity and the local orientation of the topography, it is possible to make a local application of the Markland test and consider the possibility to identify the sector where you can have a critical orientation of discontinuities with respect to the local topography. That means that you can have several sectors, for example, this one or this one, in which the local orientation of the discontinuity can be can isolate a block, and these, for example, are the sector. This is a sector in which there is a higher probability of the detachment of a block. At the end, this is an example of the results of ROCA, considering several possibility of failures that are the planal failures, also the flexural failures, or the wedge failure. The wedge is when you have a couple of discontinuity that create a wedge. The software is able to detect the most critical orientation or combination of families of joints, and put on your digital outcrop model, the sector in which there is a higher probability of this critical orientation of these families of joints. And this is a good starting point to, for example, make an estimation of the possible volume of the unstable block. We use more or less the same application. The procedure is a little bit different, and we will see in the next slides, to study the Galivaggio rockfall. Okay, in this video acquired by the University of Milano Bicocca. Please have a look in particular in the upper part of the slope. This camera acquired the moment where we had the failure of this quite large, okay, you see? So this is the failure of the block, okay? This sector was monitored because there is a sanctuary at the base of the slope, but also an important road that is a connection between Italy and Switzerland, okay? So this sector, the presence of this instability was known, okay, and the Lombardia region, the Geological Survey of the Lombardia region, and the Regional Agency for the Environmental Protection coordinate a detailed study of this slope, and also implemented a monitoring solution. And so this is a model of the unstable area acquired before the failure, and this is the model acquired after the failure. So you can clearly recognize the position of the original position of the block that failed. Okay. Then what we did, so before the failure, the Geological Survey of Lombardia asked us to make an estimation of the volume. You clearly see the presence of very, very large discontinuity. For example, this one, but also this one, okay? So they are quite evident, okay? So starting from this digital outcrop model, in particular, my colleagues of the University of Pavia, Niccolò Menegoni, made an identification of the main discontinuities. You can see these discontinuities mapped in these two images, and of course, working with the digital outcrop model, there is the possibility to remove the area outside this sort of wedge made by the intersection of these three discontinuities, and make an estimation of the volume. Okay. So before the failure, the estimation of the block was, you see, 80,000 cubic meters, but after the failure, making a dam of difference, we measured a lower volume of the failure. To make a very, very detailed comparison of the two models, we acquire many ground control points, even on a vertical slope. It is not easy to make it. We use a camera and a total station to measure points that then we are able to recognize on our slopes. And once we have these points, we use these points to couple correctly the two models to have the possibility to have a very, very detailed digital dam of difference. So at the end, once we have the possibility to make this very, very detailed comparison, what we saw, we recognize that the larger part of the volume of the difference of the volume was related to the presence of this block that in the study before the failure was considered also part of the possible failure. Okay. Then after the failure, we had the possibility to see that just this part of the area failed. Okay. And this block is still in this sector. So considering the volume of this sector, the total difference is very, very limited. And at the end, the difference, there is less than the 10%, is related to the fact that originally the surface of this wedge, what was considered, was evaluated, considered a planar surface and not, of course, a more complex surface. So at the end, we can say that the estimation has been a good estimation of the unstable block, and this is an example of what we can do using digital outcrop models and multi-rotor. As I mentioned before, the multi-rotor are the best solution when we are working with vertical outcrops. Fixed wing can be used for gentle or moderate slope. Since we are a research institute that works not only on landslide, but also on river and debris flow, okay, so different geohydrological processes, I have just a few slides to show how we can use, for example, to study the river dynamic. So this is an orthophoto of 2004. This orthophoto has been acquired using an aerial LiDAR. You can recognize the presence of this town that is called Prato Regio, okay, and the presence of the main canal, okay, of this brighter multi-canal river that is called Orco, okay. This is the same area acquired in 2007. You can see again, okay, the position of this main canal, and this is the same sector acquired in 2015 using a drone. Since these are three digital terrain models, there are the possibility to estimate the dam of difference, okay? And this is, for example, the dam of difference between the 2004 and 2007. And this is the dam of difference between 2007 and 2015. You can clearly recognize that this negative area is related to a migration. You can better see in this image. So between the 2007 and 15, we have a migration of this sector of the canal of more than 100 meters. That is an evidence that the Orco River is very, very active and dynamic. And again, also in this curve, we have a migration of more than 90 meters, unfortunately, in the direction of the Prato Reggio village that is more or less in this position. So the point is that we are using also UAV to study the river dynamic because when we have rivers that are characterized by this migration, they can create a real danger for towns that are very, very close to the position of the river. The same approach can be done, for example, if we have to study debris flow. Okay, so this is an example of the debris flow that occurred in an alpine valley, and you clearly recognize using a dam of difference. So again, if we have two digital terrain models, once acquired before the debris flow and once acquired after the debris flow, you can recognize, like in this part, in brown, the deposit that is related to the activity of this debris flow. Again, this is the section, the cross section of the canal before the debris flow and after the debris flow. That is quite clear the effect of the debris flow and the deposit that the debris flow created. So we are more or less at the end of my presentation. Just to point it out that if you are interested, of course, there are many papers published on the study of UAV. This is just a couple of papers that I publish, and the most important, I publish many, but this can be useful if you want to have a general overview on UAV. And the final slide, just to inform you that I'm one of the scientific coordinator of the IAG summer school. That is an IAG for PhD student that we organize on engineering geological topic that we organize every year in the Aosta Valley region. And the title of this summer school is The Role of Geological Model for Geohazard Management and Infrastructure Design. And the participation of the school is free of charge. And there is already the possibility to submit the application for the selection. So thank you very much. And if we have questions or we can discuss about that.
Thank you very much, Daniele. It was very enlightening for us. It's another part of geology in which we are not necessarily highly exposed. So I open the podium for questions from the audience. I don't see the class, but somebody in the class.
Yeah, do you see any underwater applications for this as well?
So I work in Torino, that is very, very close to the Alps and not so close to the sea. But I have experiences also in underwater applications. So for underwater application, in the past, we use a side scan sonar to obtain a 3D model of our area of interest. And using a multi-beam or a side scan sonar, we have the possibility to create a digital terrain model, and starting from this model, for example, to map also underwater landslides or to identify changes that can be related to the evolution of, for example, the slope stability also in underwater condition. So the approach is more or less the same, considering the part of the dam of difference and considering the use of a sequence of digital terrain model to study the evolution of a particular area. Of course, probably is not so easy to acquire a sequence of image and create a digital outcrop model, but could not be impossible.
Another question here.
Yes.
Does the weather condition affect the resolution of any of the equipment used?
Sorry, could you repeat because I?
The weather condition.
Okay. Yeah.
Does it affect any?
Yeah. So thank you. This is a good question. Of course, in particular with smaller UAV, the weather condition is important. You can fly it only in good weather conditions. Okay. So without rain and with a good visibility. Yeah. This is quite clear. Of course, this can be a limitation, but on the opposite side, the possibility to fly more or less whenever you want make easy to wait for a good weather condition. Yeah.
Okay, in terms of this weather condition, let's say there is a limitation. Which of these equipment would you suggest to be used?
Sorry, but you have to speak a little bit loudly because it's not easy for me to.
What she's asking is,
Okay.
If you have limitations of climate, which of the equipment will you use?
Okay.
How do you define which one is the one that is needed?
So, okay. So in the market of drones, there are also drones that are able to fly with, for example, light rain. Okay. So it is a part of the limitation can be solved use more expensive drone, but consider that if there is a limitation in terms of visibility, the use of visual camera is not the right solution. Also, the laser scan can work in bad weather conditions, but in bad weather condition, you have a lack of the response of the laser. So if you are really obliged to work in bad weather condition, probably the use of radar is the only possible solution. But small UAV equipped with radar are very, very uncommon. Okay, so we use, for example, synthetic aperture radar image to study the effect of floods, but this is a satellite solution, not a drone solution. Okay, because the availability of synthetic aperture radar on drones are very, very limited. Just so now in Italy there is another research institute that is working on the development of a drone equipped with a SAR, but yeah, this is very, very uncommon. So what I can say is that probably if you are in the bad weather condition, you have to wait if you want to work with drones, because it's not just a problem of payloads, but it's a problem of the user and the pilot of the drone. Yeah, also problem of safety. So I think that this is probably one of the main limitation of the use of drones. Yeah, the bad weather condition with more or less any payload. Okay. I don't know if I answered to the question.
Yes, you did.
Thank you very much. Somebody else has a question?
Do we have time for another one?
Yes, please.
Yeah, so I have a question, more about the analysis of the data afterwards, especially if you work in areas where you have forest or a lot of vegetation.
Yep.
How do you clean this data if you want to see the rock surface, or can you do it?
Yeah, okay, so thank you. This is a very, very good good question. I had an example, but I didn't have the time to show you. So the point is that if you are working with images, okay, the sequence of image will be a sequence of image of the top of your tree, okay? Using the structure from motion, you have the possibility to create this digital surface model, but if you are not able to see the ground, okay, your model will be a model of the top of the vegetation. You can remove it, of course, but removing this information, you will have an area without the information, okay? So using just images, that means using the cheapest drone, if you are working in an area that is strongly vegetated, you will have several sectors without any information about the ground. In these sectors, the only possibility it is the use of a laser scanner, okay? And in particular, a laser scanner, the most expensive are full waveform. That means that for every beam, you have several reflections. The first reflections are reflection of the vegetation, so the first targets that the beam hit. But at the end, you can also reach the ground, okay? The laser scanner is very useful because you have the possibility using this full waveform laser to have these several echoes, and the software are able to make an analysis of these echoes and recognize the echoes that belongs to the ground with respect to the echoes that belongs to the vegetation. Using this system that are very, very expensive solution, at the end, you have the possibility to make a classification of your point cloud and remove the vegetation and obtain just the ground data. Yeah, this when the vegetation is very, very important, very often just the use of image is not enough to obtain a very good representation of the ground, and the LiDAR, so the laser scanner, is probably the only solution.
Thank you.
I have one question.
Another question here?
Yes?
So the question is that is it possible to distinguish between the bedding plane and the fracture? So what I learned from your one of figure, so the discontinuity you were saying, that was the bedding plane.
Yeah, so
So how you will recognize it?
so in many outcrop, it is quite evident what is the bedding and what is, so for example, in this outcrop, it's quite evident that this is the bedding, okay, and these are discontinuities, okay. Of course, if you are working with sedimentary rocks, this could be more easy, okay. If we are working, like in this case, in metamorphic rocks, not always is easy to recognize the bedding and distinguish the bedding with respect to the other discontinuities. For the study of the stability, not always is important to make this distinction, but of course, if you are able to do it, is important. In my experience, I prefer to make the map of discontinuity manually, okay, and not using automatic systems, because if you are doing these analysis manually, it is also more easy to make this difference between bedding and the other discontinuity. Of course, if you are asking to a tool, for example, there are many cloud compare tools that are able to identify the discontinuities. Of course, these tools are not able to recognize the bedding with respect to the other discontinuities. So there is if you want to make a very detailed analysis, I think that until now, the role of skilled geologist is important to have a very detailed mapping of this discontinuity, and also the recognition, for example, of the bedding, like in this case.
So we cannot be completely overcome by AI or something like that. You need geology.
I hope to continue to work until my retirement, and then we will use the AI. Yeah, but I think that we will still have a work to do. Okay, in particular, if we want to make a very detailed analysis. Until now, the automatic application, we are also working the developing of automatic applications, but they are not so. So the performance is not so great. There are many evidence of recent improvements, but I think that a manual identification of discontinuity is still a good solution. Yeah, probably in the future, yeah, we will lose our job. Yeah.
Thank you.
Okay, thank you very much. I think we don't have sufficient time for more questions. So again, thank you, Daniele,
Yeah,
and
you're welcome.
hope to see all of you in the next semester.
Okay.
Thank
Bye-bye.
you. Bye-bye.
Thank you.